Slash API cost and speed up LLM calls. You will learn a small, testable pipeline that saves requests and reduces latency. By the end, you can cache repeated prompts, enforce a 2 RPS limit, and normalize near duplicates to boost cache hits. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced in simple Python. Caching and rate limiting cut 2 things you care about. First is cost per request, because fewer calls means lower billing. Second is latency for repeat queries, because a cache can return answers instantly. The trade-off is memory and freshness. More cached entries use more memory and risk returning stale replies. At scale, this can save tens of thousands in monthly spend on medium-sized workloads when hits exceed 30%. The intuition is simple. Cache stores responses keyed by prompts, so repeats are cheap. Rate limiting spaces out live calls to stay under provider quotas and avoid throttles. Where this shines is in predictable traffic with many repeats. It is weaker for single shot, real-time queries where freshness matters most. We will build a minimal pipeline that simulates an LLM, adds an LRU cache, schedules requests into fixed windows, normalizes keys for near duplicates, and then combines everything into a single flow before we test it. This snippet simulates an LLM reply with a tiny deterministic delay. It stands in for a real API, so we can test caching and throttling without costs. The simulated call returns the same answer for the same prompt every time, which makes it trivial to validate cache hits. A small delay parameter controls how long the fake LLM waits, and increasing that delay emphasizes the benefit of returning cached entries. This is useful for measuring perceived latency reduction and for debugging the pipeline before you switch to a real provider. Next, we add caching and observe hits. This snippet adds an LRU cache and reveals a concrete cache hit. It stores responses keyed by prompt, up to a maximum number of entries, and evicts the least recently used when full. The snippet demonstrates a hit by calling the same prompt twice and showing the second response comes from cache rather than the simulated LLM. The adjustable parameter here is cache size. Increasing the size raises the hit rate and reduces calls to the LLM, while decreasing it saves memory but increases misses. Use a size that balances memory and expected prompt variety. Next, we plan requests into fixed windows to enforce the limit. This snippet plans requests into fixed window slots for a 2 RPS limit. It assigns each request to the current window based on the clock and ensures only a fixed number of requests leave the system per window. If a window is full, the request waits for the next slot, introducing predictable queuing. The key parameters are the window duration and allowed requests per window. Shorter windows give finer control, but require more checks. Lower allowed requests reduces burst cost, but increases queuing delay. So tune to match your SLA and provider limits. Next, we normalize keys, so near duplicate prompts map to one cache entry. This snippet normalizes keys so near duplicate prompts map to one cache entry. It applies simple steps like lowercasing, trimming white space, collapsing repeated spaces, and removing punctuation, so prompts that differ only by formatting become identical keys. This boosts cache hit rate for real user text that varies by casing or punctuation. The adjustable parameter is how aggressive the normalization is. More aggressive normalization increases hits, but risks merging genuinely different prompts. Choose normalization to match your domain and how strict you need exact wording to be. Finally, we combine caching and rate-limited batching into a minimal pipeline. This snippet combines caching and rate-limited batching into a minimal pipeline. It takes a list of prompts, checks the cache for each, and groups the cache misses into batches that are released according to the fixed window planner. Responses from the simulated LLM are written back into the cache after normalization. The main knobs are cache size, normalization aggressiveness, and the rate limit parameters. Increasing batch size can improve throughput, but may increase per request latency. Tightening rate limit reduces cost, but increases queuing. This combined flow shows the real interplay between hit rate, latency, and quota control. Recap. First, caching returns repeated answers instantly and saves cost. Second, rate limiting prevents quota errors and smooths traffic. Third, a caveat is stale or over-normalized cache entries can return wrong answers for new contexts. Next step, stale this pipeline by swapping the simple cache for an approximate nearest neighbor store, and tune its index parameter to trade recall for search speed. If practical AI engineering helps you build reliable systems, subscribe and watch the AI engineering videos.